Hello. Okay. Well, thanks, Matt, and the OCB workshop organizers for inviting me to give a talk today. And this was Matt's suggested title, Intraseasonal Variability in Driving Physical and Biogeochemical Dynamics in the Southern Ocean. And I just changed it to subseasonal because usually the atmospheric community refers to intraseasonal variability to scales longer than the synoptic scale, and although within a season. And actually I am interested, and my research focuses on these short temporal scales on the atmospheric synoptic scale. So this is mostly work that I've done during my PhD at Scripps, funded by a NASA fellowship. And it's in revision, and hopefully I will be able to resubmit soon. For this talk, we get away from the ice. There's no ice here over Antarctica. And for those not so familiar with the system, we know that the mean circulation in the Southern Ocean is primarily set by these strong westerly winds and the eddy field. And these, together with the solubility pump and biological pump, result in great amounts of heat and carbon uptake. But as Matt was saying, we do not know really what is even the phasing of the seasonal cycle or the amplitude when it comes to carbon fluxes, especially related to biologically mediated carbon fluxes. So we think some of the uncertainties in the models and the observations comes from the fact that this region is a highly dynamic region. So we have a great deal of variability in the wind field on these synoptic storm timescales, and a vigorous eddy field that both, contribute to this system with very weak stratification. And, the flow is primarily strongly influenced by topography. So I think a good way to look at the system and, subseasonal variability is to frame it, by externally forced variability. This is the atmospheric weather, these large-scale synoptic systems that steer up the upper ocean on these spatial scales of hundreds of kilometers and inject variability in the system on short temporal timescales, like between 2 and 10 days. And then we have the oceanic weather, the internally forced variability that may be there even without atmospheric forcing variability. And this is what we see in these, these ocean color images, the mesoscale eddies and the submesoscale filaments around the eddies. And for the purposes of this talk, I'm just going to focus or highlight, if I have time, some of the few submesoscale studies that are coming out from field observations. But I do that because mostly the submesoscales also operate on these very few, very short timescales. So the mesoscale and submesoscale can be dynamically very different. And one of the main characteristics of the submesoscale, as I said, it operates also on timescales of few days. And the flow is largely, there are large vertical velocities associated to it, as opposed to the mesoscale that is mostly characterized by flow, by horizontal flow. And in other latitudes, this submesoscale field is believed to be constrained to the mixed layer. So, of course, when we go and observe the ocean, we see the interaction of, the ocean and the atmosphere acting together. And, one example is here when you have, this type of front in the ocean. You'll have the wind forcing and heat fluxes that can also steer and stratify the ocean. And for instance, depending on what's the wind orientation with the frontal current, you can either enhance or suppress the frontal circulation itself. So why do we care about this? Well, aside from being very interesting phenomena, and we get to draw all these very nice and cool pictures, I think one of the main important things is that they steer the ocean and impact stratification and mixed layer depth variability on these timescales of days, which resonate with the life cycle of phytoplankton. And also because these weather perturbations, small and short temporal scales, can influence climate or longer and larger spatial scales. So a few studies tried to highlight this last point that came, and these are studies that came out from high-resolution observations of the carbonate system. This is, for example, a study by Resplandí et al. In 2014 from Carioca drifters that carried CO2 sensors, and they measured at hourly and 1 to 3 kilometers resolution. So what they tried to point out here, they did analyze the data filtering the large scales and the long temporal scales, and compared it to some, so looked at the variability in this range of scales, and they find that actually the amplitudes of this variability is about a third of the variations associated with a seasonal cycle. So they conclude that the small scales matter, and we may be, the changes we see in the seasonal cycle may be largely impacted by these small scales. So, and there's also the study by Monteiro et al. In 2015 that they combined a metric for what they call the seasonal cycle reproducibility, which is essentially the fraction of variance that is explained by the seasonal cycle. So all that you see in green and yellow here are regions where really, based on satellite chlorophyll, there's very little variability that can be explained by the seasonal cycles. So they combine this with glider observations at a quasi-fixed location, that sample also a very high resolution CO2. And so they did an experiment, computing the mean at different sampling intervals, and they came out with this percent or probability distribution for the mean as a function of the sampling interval. So in essence, what they suggest is that these uncertainties in the seasonal mean CO2 fluxes may arise from undersampled and unresolved dynamics. So my research mostly focused on these atmospheric weather impacts, and so we know that this stormy weather comes along with very deep mixed layers and gloomy conditions. And so what does this mean for phytoplankton? Essentially, the paradigm for phytoplankton bloom development is that these deep mixed layers and presumably deep mixing might remove phytoplankton from the well-lit zone and reduce their potential to grow. But we know that changes in the mixed layer depth can also alter the nutrient supply. As mixed layer depth deepens, might enter nutrients, it might alter organisms' interactions, and so on and so forth. So in 2015, in Carranza and Guille, we showed that what is a chlorophyll response from, as we see it from satellites, to high wind events on daily timescales. So we combined these observations with mixed layer depth observations from Argo floats. So here you see that high wind speeds are correlated with deep mixed layers. So the wind mixing seems to be penetrating to the base of the mixed layer. And also this was consistent with high winds correlated with high chlorophyll, which is consistent with entrainment from below the euphoric zone. So one might think that this entrainment could be entraining iron, impacting on growth scales, and there's a subsequent study from Nicholson et al. In 2016 from a modeling study where they tried to show that this storm-driven mixing enhances primary production when you consider a subsurface layer of enhanced mixing. But we went further on with the correlation analysis, and when we looked at lagged correlations, the correlation vanishes at 3-day lags. So if the signal was an impact of winds mixing iron and impacting on growth rates, we would expect to see a higher correlation at a 3-day lag. And this is based on ship incubation experiments and what you might expect to, when you might expect to see a change in the chlorophyll A response when you add iron to a water sample. So we think that rather maybe this wind-driven entrainment is enhancing chlorophyll A from a subsurface maxima. And this is something we can test now with all the bio-optical profiles that are coming out. Sorry, it came out. From the profiles that are coming out from SOCOM, and there's a bunch of other profiles from different cruises, and also elephant seals that carry fluorometers. So this is just 2 examples of elephant seal trajectory. So you see depth versus times and the chlorophyll A signal, and the white line is the mixed layer depth. So there were 2 patterns essentially that emerged. One was that there is chlorophyll A variability within the mixed layer, and also the ubiquitous presence of this deep chlorophyll A maxima. Oops. So so essentially, before I jump into the results, I want to point out that the mixed layer that is homogeneous in density is quite different from the mixing layer that is actively turbulent. So we think that these varying levels of turbulence within an homogenized mixed layer is what may be causing structure within the mixed layer in the bio-optical profiles that we observe. And there is theoretical work that has shown that it's really the trade-off between the mixing timescales and the biological photoadaptation that might determine whether you can form a gradient or not within the mixed layer. So here we quantified this variability using the standard deviation index that compares variability within the mixed layer with variability for all mixed layers across the region. And we can clearly see that for bio-optics, there's a much greater variability than, for example, for temperature. So I think this is telling us that a lot of this variability is driven by biology, at least to first order. So we did looked at the bio-optical profiles and fitted different functional forms to them to characterize this deep fluorescence maxima. And we did that for chlorophyll A fluorescence and backscattering that we have from the floats, and compared it with the mixed layer depth. So one thing that was pretty impressive was that only 40% of these profiles showed chlorophyll A fluorescence or backscatter mirroring density. But most of the times we see all these different type of structures and Gaussian structures find within the mixed layer. So this is, for example, the percent of profiles that showed this deep fluorescence maxima, and these aren't, the large deep fluorescence maxima that we often see in the subtropical regions, but they do show, and they are above the noise level, and they had peak prominences between 0.1 in the winter and 0.7 in the summertime. So the depth of the deep fluorescence maxima more often was found at the base of the mixed layer, but also, we saw this great amount of profiles that showed it within the mixed layer. And this was true regardless of the mixed layer definition, even for the most stringent criteria that supposedly is it's a better proxy for the mixing layer. At least 20% of the profiles show the maxima within the mixed layer. And when you segregate between winter and summer data, the difference becomes much larger. So what can we learn about biological and mixing timescales from this? So we think that the existence of these gradients is telling us that biology acts on much more rapidly than the mixing timescales that are homogenizing the surface mixed layer. So on the basis that, the storms are one of the dominant forcings of the mixing in the upper ocean, as I was saying, we think that, these varying levels of mixings that we may find between periods of quiescence between storm events might be long enough to allow biology to take off and create these gradients, perhaps in regions where mixing is minimal. So can we constrain biological timescales of stratification based on these storms timescales? So this is the storm cycle, the duration of a storm and the duration of an interstorm period that we can compute from satellite wind data. And then we have the profile structure statistics from the floats. So essentially, the rationale is that we assume that the fraction of homogeneous profiles will be the time during a storm plus the time it takes biology to take off over the storm cycle. So we did that, and we computed the recurrence of storms. So we have one storm every 7 days arriving at each location, and these storms tend to last 3 days, and most importantly, the interstorm period tends to be a little bit longer, on the order of 4 days, and there's a seasonality to it. So we see storms get less frequent, and there's longer interstorm periods in the summer versus in the winter time. So when you combine this with the overall statistics for Bio-optical profile structure data, we see what this is telling us is that biology restratifies in less than 1 to 3 days. We also looked at wind profile matchups, so the wind at the closest time of the profile location. And so the picture was consistent. Wind was correlated, the mixed layer deepens as the wind increases, and this is the variance and chlorophyll A backscattering signal that also is telling us that biotics get homogenized for larger wind speeds. What happens after a storm? So we looked at each profile location, the history of winds, during the last 10 days, before the sampling time. So we see that mixed layer depth decreases after a storm, and this is also consistent with the fact that variance in bio-optical properties increases within the mixed layer. So I plotted here also peak prominence, and the peak prominence also increases. And so if you feed a line here, you get chlorophyll A-based growth rate of 0.31 day. 0.31. And this implies that biological, again, stratification operates on timescales of less than 3 days. So the implications are that hydrographic mixed layers are not mixed in bio-optical properties and potentially other tracers and even organisms. So this might imply that biological timescales for growth might be shorter than previously thought, and what we tend to observe from shipboard incubation experiments, which means that probably southern oceans phytoplankton is well adapted to the light nutrient conditions and cold temperatures. And the seasonality and asymmetry that we see in storm timescales suggests that atmospheric weather can probably have a net effect on annual means. So I guess I'm out of time to talk a little bit about, I just wanted to highlight some studies about the sub-mesoscale, which also operates on scales of a few days. And I think the things I want to point out about these studies are, this is a modeling study that shows sub-mesoscale patchiness in regions where we see also that are hotspots for mesoscale eddy activity. And one of the interesting things from this study is that it seems to be enhanced at depth as well. So these sub-mesoscale features might be able to reach iron from below the mixed layer. And then there's a study by Biglione et al. That just came out in over Drake Passage that also shows that there seems to be highly active sub-mesoscale field in the summertime, as opposed to other latitudes that have found that the sub-mesoscales dynamics might be playing a role in the winter time. And this is a study by Zachary Eriksson that's probably here that also suggests that this sub-mesoscale might be subducting chlorophyll A and creating some of these chlorophyll A maxima that we observe at the base of the mixed layer. I think I'll jump to the conclusions. Yeah, so essentially synoptic winds impact the mixed layer depth and chlorophyll A variance. And I think you can go through it, and I'll take questions if I have time.
That was super interesting. Thank you. I was curious about whether you thought that the fact that phytoplankton are not in fact dissolved like temperature or salinity, and they're particles that may have a sinking rate, might contribute to the apparent restratification of the biological signal.
I mean, we suggested that the mixing could be a possibility, but of course there are many other, I know some can swim or might be creating this accumulation at the base of the mixed layer.
A question over here, Philip Boyd, IMAS, Australia. It seems like in this, the sort of cycles you show where you're deepening the mixed layer and then you're restratifying again, there are a large number of different things happening. So the first one is obviously, as you deepen the mixed layer, you're going to dilute the stocks that are in it. And then as you re-stratify the mixed layer, you're going to detrain some of those stocks out of it. And then also you have this unique photophysiology of the Southern Ocean phytoplankton. So again, if you're going to use fluorescence or chlorophyll, you've got biomass in there, but you've also got photophysiology.
Yeah, well, we only, I forgot to mention, but we only use nighttime data for that reason, and we also looked at the backscattering signal. So all the lines that are optical backscatter, that supposedly is another proxy of phytoplankton biomass. But yeah.
But again, regardless of using the nighttime profiles, all that does is get rid of the diurnal quenching signature, but you still have this distinctive photophysiology of the Southern Ocean phytoplankton. So I was just wondering, in your analysis, were you able to tease apart the roles of dilution, the role of detrainment, and then potentially the role of the physiology and how it might influence or mask what was happening with the biomass?
Yeah, I mean, I'm not sure how right now, but yeah. I mean, we've looked at the daily variations too in both this subsurface chlorophyll maxima in chlorophyll fluorescence and backscattering, and the two went, we saw the maxima in both we saw the maxima due to the quenching, but it was also in the backscattering signal.
Yep, that's great.
Hi, thanks for the great talk. I was wondering, you showed fluorescence data and backscatter data. I don't think you showed the ratio of them anywhere.
The what?
The ratio between fluorescence and backscatter?
Yeah, and the reason is because we are looking at variability, and so it gets complicated when you have a ratio of two things varying. So we prefer to show, the two signals.
Yeah, I was just thinking that might help you get at kind of photophysiology effects, or depending on how you interpret it, what species you have. I mean, it's just another handle you might be able to use.
I tried to look at that, but we thought it was easier to interpret just to look at the two variables separately.
Hi, Samantha Sidlecki from University of Connecticut, right over here. I was wondering if you've thought about it was really interesting, the storms, winter storms, and the influence on phytoplankton. If you've thought about whether or not if you needed just like one big, really intense storm, or if, a lot of little storms, so the frequency of them and which one's more important.
Actually, I didn't mention it, but we defined a storm as a wind, as a time period when we had wind speeds greater than 10 meters per second that lasted for at least 3 days. And we had done a lot of sensitivity studies to look at, how that threshold, the change on that threshold, modified the results. But essentially that 10 meter per second threshold is what you see when in studies that have looked at these storms, tracking them, is essentially where you see the PDF ramping up for the wind that you would expect to find at the center of one of these storms. And yeah.
Okay, let's thank Magdalena again.